Welcome to our channel Knowledge Catch. Thank you for joining us today. As we dive into the world of switching, VLANs, and STP, it's crucial to understand the vital role these concepts play in our connected world. Whether you're streaming videos, sending emails, or collaborating globally, your network infrastructure makes it all possible. In this video, we'll demystify switching, VLANs, and STP, giving you the knowledge to design, implement, and manage efficient networks. Our goal is to empower you to take control of your network environment, meeting both today's and tomorrow's demands. By the end of this session, you'll have a solid foundation in these critical networking concepts, ready for real-world application. This content is tailored for the CCNA exam and covers about 25% of the syllabus. We've worked hard to bring you this guide, so if you find it helpful, please like this video and subscribe our channel for more videos like this. Let's get started and unlock the full potential of your network. Let's understand agenda for today. We'll explore 8 main topics. First, we'll cover the basics of Ethernet switching, where you'll learn how switches manage data using MAC addresses and keep everything running smoothly. Then we'll dive into VLANs and Trunking, explaining how to divide and manage network traffic efficiently. Next, we'll look at the Spanning Tree Protocol (STP), which keeps our network free of loops. We'll also discuss EtherChannel, a way to combine multiple connections to make a stronger link, just like braiding several ropes together for strength. We'll then move to Inter-VLAN Routing, which is about making sure different network segments can talk to each other. After that, we'll go over security features to keep our network safe. We'll explore advanced technologies like smart networking tools that can predict problems before they happen. Finally, we'll discuss troubleshooting and best practices to keep your network in top shape. Each section builds on the last, making sure you get a complete understanding of Ethernet switching. Let's get started. Ethernet switches are fundamental to modern networks, operating at layer 2 of the OSI model to manage data transmission using MAC addresses. Each switch maintains a MAC address table, which maps MAC addresses to specific ports. When a frame arrives at a switch, the switch learns the source MAC address and updates its table. It then checks the table for the destination MAC address to determine the correct port for forwarding the frame. If the destination MAC address is not found, the switch floods the frame to all ports except the one it came from, ensuring it reaches its destination. Each switch port is a separate collision domain, meaning that data collisions are confined to individual ports rather than the entire network. This separation significantly reduces the likelihood of collisions and enhances network performance. All ports on a switch are part of the same broadcast domain unless VLANs, virtual local area networks, are implemented. A broadcast domain includes all devices that can receive broadcast frames sent by any device within that domain. By using VLANs, you can segment the broadcast domain, limiting broadcasts to specific VLANs and reducing network congestion. Understanding these basics helps optimize network performance and lays the foundation for more advanced concepts. Now let's explore different switching modes and memory types. Ethernet switches use different modes to handle data efficiently. These modes include store and forward, cut-through, and fragment-free. In the store and forward mode, the switch receives the entire frame and checks it for errors before forwarding it. This ensures error-free transmission but introduces higher latency as the switch waits for the entire frame to arrive. Cut-through mode, on the other hand, starts forwarding the frame as soon as the destination MAC address is read. This reduces latency but sacrifices error checking, potentially forwarding corrupted frames. Fragment-free mode strikes a balance by checking the first 64 bytes for errors before forwarding, catching most errors without introducing significant latency. Switches also use 2 main types of memory: CAM, Content Addressable Memory, and TCAM, Ternary Content Addressable Memory. CAM is used for fast lookups of MAC addresses, allowing the switch to quickly determine the correct port for forwarding frames. TCAM is used for more complex operations like access control lists, ACLs, quality of service QoS, and route lookups. TCAM can store multiple bits of data and perform searches that involve partial matches, making it ideal for these advanced tasks. Understanding these switching modes and memory types is crucial for optimizing network performance and ensuring efficient data handling. Next, we'll discuss the different types of switch ports and their specific roles. Switch ports come in different types, each serving distinct roles in the network. Understanding these port types is essential for configuring and managing network traffic effectively. Access ports are used to connect end devices like computers, printers, and IP phones to the network. Each access port is assigned to a single VLAN, ensuring that the connected device can only communicate with other devices in the same VLAN. This configuration is straightforward and ideal for environments where devices do not need to interact with multiple VLANs. Trunk ports carry traffic for multiple VLANs between switches, or between a switch and a router. Trunk ports use tagging methods like 802.1q to identify which VLAN each frame belongs to. This allows VLANs to span across multiple switches, maintaining VLAN segmentation, and ensuring consistent network performance. Routed ports are found on Layer 3 switches and provide Layer 3 functionality. These ports are used for routing traffic between different VLANs or subnets. By configuring routed ports, you can eliminate the need for a separate router, simplifying network design and improving performance. Port security is a feature that limits the number of MAC addresses that can connect to a port. This helps prevent unauthorized devices from accessing the network, enhancing security. Power over Ethernet (PoE) allows the switch to provide power to devices like IP phones and wireless access points over the same Ethernet cables used for data transmission. This simplifies installation and reduces the need for additional power supplies. Understanding these port types and their configurations enhances network flexibility and security, ensuring efficient traffic management and robust network performance. Next, we'll explore VLANs and their importance in network segmentation. VLANs, or virtual local area networks, are essential for segmenting network traffic logically, which improves security and performance. VLANs allow devices to be grouped logically rather than physically, providing greater flexibility in network management. VLANs are categorized into different ranges. Normal VLANs range from 1 to 1005, while extended VLANs range from 1006 to 4094. The native VLAN is the untagged VLAN on a trunk link, with VLAN 1 as the default. However, it's a best practice to change the native VLAN to another ID to enhance security. Voice VLANs are used to separate voice traffic from data traffic, often with quality of service (QoS) settings to ensure clear and reliable voice communication. To create a VLAN, you use the command VLAN followed by name, VLAN name. Assigning ports to VLANs involves setting the port to access mode with switch port mode access, and then assigning it to the desired VLAN using switch port access VLAN ID. For voice traffic, you use the command switch port voice VLAN ID. VLANs help manage network traffic by isolating it, enhancing performance, and providing flexibility in managing network resources. They reduce broadcast domains, which minimizes network congestion and improves overall network efficiency. Understanding the different types of VLANs and how to configure them is crucial for effective network segmentation and management. Next, we'll discuss VLAN types and membership methods. There are various ways to assign VLANs to ports, depending on your network needs. Port-based VLANs assign specific ports to a VLAN, which is the most common method. Protocol-based VLANs assign VLANs based on Layer 3 protocol types, such as IP or IPX, to segregate different types of traffic. MAC address-based VLANs assign VLANs based on the device's MAC address, regardless of the port they connect to. Dynamic VLANs use VMPS or radius to assign VLANs dynamically, providing flexibility in environments where devices frequently move. Private VLANs further segment a VLAN for additional isolation, enhancing security and providing more granular control. Understanding these VLAN types helps tailor network segmentation to specific needs, ensuring efficient and secure operations. Next, we'll cover VLAN configuration and best practices. Creating and managing VLANs involves a few specific steps, but don't worry, it's straightforward. To create a VLAN, use the command VLAN followed by the VLAN ID and name followed by the VLAN name. This sets up a new VLAN with an ID and a name you choose. Next, to assign ports to a VLAN, Use the command switch port mode access and switch port access VLAN followed by the VLAN ID. If you need to set up a VLAN for voice traffic, you can use switch port voice VLAN followed by the VLAN ID. To check if everything is set up correctly, you can use verification commands like show VLAN brief and show interfaces switch port. These commands help you see the VLAN configurations and ensure that all settings are correct. There are a couple of best practices to follow. First, avoid using VLAN 1 for user traffic because it's the default VLAN and can pose security risks. Second, use clear and meaningful names for your VLANs. This makes it easier to manage and troubleshoot your network. Properly configuring VLANs helps segment your network efficiently, which improves performance and management. Next, we'll talk about VLAN trunking and how to configure it. VLAN trunking allows VLANs to span multiple switches, maintaining consistent configurations across the network. The 802.1q standard tags frames with VLAN IDs, allowing switches to identify the VLAN each frame belongs to. ISL, an older Cisco-specific method, is now mostly obsolete. The native VLAN is the untagged VLAN on a trunk link, defaulting to VLAN 1, but it's recommended to change this for security reasons. Dynamic Trunking Protocol (DTP) automates the negotiation of trunk links between switches. To configure a trunk, use the command switch port mode trunk and specify allowed VLANs with switch port trunk allowed VLAN followed by VLAN list. For example, switch port trunk allowed VLAN 10, 20, 30. Trunking ensures that VLAN traffic can traverse multiple switches, maintaining network segmentation and performance. It's essential for environments where VLANs need to be consistent across several switches, such as in large enterprise networks. Understanding and configuring VLAN trunking is crucial for effective network management. Next, we'll explore the VLAN Trunking Protocol, VTP. VTP, or VLAN Trunking Protocol, manages VLAN information across switches, simplifying VLAN management. VTP operates in three modes: server, which creates and manages VLANs, client, which receives VLAN information from servers, and transparent, which forwards VTP messages without applying changes. VTP has three versions, with VTP v3 supporting extended VLANs and offering enhanced security features. All switches in the same VTP domain share VLAN information, ensuring consistency across the network. VTP pruning reduces unnecessary VLAN traffic on trunk links, optimizing bandwidth usage. Configure VTP with the command VTP mode, server client transparent. VTP simplifies VLAN management across multiple switches, making it easier to maintain consistent VLAN configurations and reduce administrative overhead. Next, we'll discuss the basics of the Spanning Tree Protocol, STP. Moving on to the section on Spanning Tree Protocol, STP Basics. Spanning Tree Protocol is essential for preventing network loops, which can cause significant disruptions and inefficiencies in a network. STP operates at Layer 2 of the OSI model and follows the IEEE 802.1d standard. STP ensures there is only one active path between network devices by creating a loop-free logical topology. It selects a root bridge, which is the switch with the lowest bridge ID, a combination of priority and MAC address. All other switches then determine the shortest path to the root bridge using path cost. Ports in STP can be in different states: blocking, listening, learning, and forwarding. Blocking ports do not forward frames to prevent loops. Listening ports are preparing to forward frames, but do not yet have MAC address information. Learning ports start collecting MAC addresses, and forwarding ports actively send and receive frames. By understanding STP, you can keep your network stable and efficient, preventing issues like broadcast storms and ensuring smooth operation. Let's now delve into the roles of ports in STP and the concept of BPDUs. In Spanning Tree Protocol, each port has a specific role to play in maintaining a loop-free network topology. The root port is the port with the best path to the root bridge, essentially the port that the switch uses to reach the root bridge. Designated ports are selected on each network segment. These ports handle the forwarding of frames for that segment. Non-designated ports, on the other hand, are in a blocking state to prevent loops. Bridge Protocol Data Units (BPDUs) are the messages exchanged between switches to share information about the network topology. BPDUs contain details like the bridge ID and path cost, and they are sent every 2 seconds by default. These messages help switches identify the root bridge and establish the shortest paths to it. Understanding the roles of ports and the function of BPDUs is crucial for maintaining an efficient and stable network. Next, let's move on to Rapid Spanning Tree Protocol, RSTP, which enhances the original STP for faster convergence. Rapid Spanning Tree Protocol, RSTP, is an enhancement of the original STP, defined by IEEE 802.1W. RSTP improves network convergence time significantly, usually achieving convergence in 1 to 5 seconds. RSTP introduces new port roles: root port, designated port, alternate port, and backup port. The alternate port provides a backup path to the root bridge, while the backup port provides a redundant link to the same segment. Port states in RSTP are simplified to discarding, learning, and forwarding. Discarding replaces the blocking state from STP and ensures no frames are forwarded, preventing loops. Learning and forwarding states function similarly to those in STP. RSTP uses a proposal and agreement mechanism to quickly transition ports to the forwarding state. Edge ports in RSTP immediately transition to forwarding, reducing the delay typically associated with STP. By implementing RSTP, networks benefit from quicker recovery from changes and improved overall performance. Now let's explore Multiple Spanning Tree Protocol, MSTP, and how it further optimizes network performance. Multiple Spanning Tree Protocol, MSTP, is defined by IEEE 802.1s and allows multiple VLANs to be mapped to a single spanning tree instance. This reduces the number of spanning trees required, optimizing the use of network resources. MSTP groups VLANs into instances. Each instance runs its own spanning tree algorithm, allowing for load balancing and efficient use of links. Switches in an MSTP environment are divided into regions, where all switches in a region share the same MST configuration. MSTP reduces the CPU load on switches compared to running separate spanning trees for each VLAN, as in PVST+, per VLAN spanning tree plus. This makes MSTP more efficient for large networks with many VLANs. By understanding MSTP, network administrators can better manage large, complex networks, ensuring efficient operation and optimized resource usage. Finally, let's look at some STP enhancements and features that further improve network stability and security. To further improve Spanning Tree Protocol, STP, several enhancements and features can be implemented to enhance network stability and security. Port fast transitions access ports directly to the forwarding state, bypassing the listening and learning states, which is ideal for ports connected to end devices like computers where there is no risk of creating loops. BPDU guard is a security feature that disables a port fast-enabled port if it receives a BPDU, thereby preventing potential loops and protecting the network from misconfigurations. Root guard prevents external switches from becoming the root bridge by placing a port in a root inconsistent state if an external switch attempts to become the root bridge, thus ensuring the network's designated root bridge remains stable. Loop guard prevents a port from becoming a designated port if it stops receiving BPDUs, protecting the network from the temporary loss of BPDU packets, which could otherwise cause loops. Unidirectional link detection, UDLD, detects and disables unidirectional links, which can occur due to hardware faults and lead to loops, ensuring bidirectional communication on a link and enhancing network reliability. Implementing these STP enhancements and features helps maintain a robust, secure, and loop-free network, ensuring smooth and stable network operations. Moving on to EtherChannel Fundamentals. EtherChannel is a technology used to increase bandwidth and provide redundancy by bundling multiple physical Ethernet links into one logical link. Imagine you have several roads connecting two cities. Instead of using just one road, EtherChannel allows you to use all the roads simultaneously, making the travel faster and more reliable. EtherChannel enhances network performance by allowing traffic to be distributed across multiple links, effectively multiplying the available bandwidth. If one link fails, the traffic is seamlessly shifted to the remaining links, ensuring continuous network service without interruptions. This failover capability is crucial for maintaining network reliability. EtherChannel can be configured for both Layer 2, switching, and Layer 3 routing scenarios, providing flexibility depending on your network's needs. By combining several Ethernet links, EtherChannel helps to avoid bottlenecks and provides a more robust and resilient network infrastructure. EtherChannel can be implemented using different protocols to facilitate the bundling of links. The two primary protocols are Link Aggregation Control Protocol, LACP, and Port Aggregation Protocol, PAGP. LACP is an open standard defined by the IEEE 802.3 AD. It allows switches to automatically negotiate the bundling of links. LACP operates in two modes, active and passive. In active mode, the switch actively tries to form an EtherChannel by sending LACP packets. In passive mode, the switch only responds to LACP packets it receives. This dynamic negotiation ensures that links are only bundled if both ends of the link agree, enhancing compatibility and reducing configuration errors. PAGP is a Cisco proprietary protocol that also automates the formation of EtherChannels. PAGP operates in desirable mode, where the switch actively tries to form an EtherChannel, and auto mode, where the switch waits for a PAGP packet from the other end to form the EtherChannel. While PAGP offers similar functionalities to LACP, it is limited to Cisco devices. Understanding and choosing the right protocol for your network is crucial for ensuring seamless integration and optimal performance. Configuring EtherChannel involves several key steps to ensure that multiple physical interfaces are correctly bundled into a single logical link. Start by selecting the interfaces you want to bundle. This is done using the interface range command, which allows you to specify multiple interfaces at once. Next, you assign the interfaces to an EtherChannel group using the channel group command, followed by specifying the mode, on active, passive, desirable, or auto. For example, to configure EtherChannel using LACP in active mode, you would use the command channel group, number mode active. This step binds the selected interfaces into an EtherChannel group. Once configured, it's essential to verify the setup to ensure all links are functioning correctly. Use commands like show EtherChannel summary and show EtherChannel port channel to check the status and details of the EtherChannel. Proper verification helps in identifying and resolving any issues, ensuring that the EtherChannel operates as intended, providing increased bandwidth and redundancy. Inter-VLAN routing is a critical concept that enables communication between different VLANs. VLANs are used to segment a network into smaller, more manageable pieces. However, for devices on separate VLANs to communicate, routing between these VLANs is necessary. Traditionally, this was achieved using a method known as router on a stick. In this setup, a single physical interface on a router is divided into multiple subinterfaces, each configured for a different VLAN. The router uses these subinterfaces to route traffic between the VLANs, effectively acting as a bridge. Modern networks often use Layer 3 switches for inter-VLAN routing. Layer 3 switches combine the high-speed switching capabilities of Layer 2 devices with the routing capabilities of routers. They use switched virtual interfaces, SVIs, or routed ports to handle inter-VLAN traffic, simplifying the network design by eliminating the need for a separate router. This approach not only enhances performance but also reduces complexity, making network management more straightforward. Configuring router on a stick involves setting up a single router interface to handle multiple VLANs. Here's how you can do it. First, create subinterfaces on the physical router interface. For example, if you have interface Gigabit Ethernet 0/1, you would create subinterfaces like Gigabit Ethernet 0/1.10 for VLAN 10 and Gigabit Ethernet 0/1.20 for VLAN 20. Next, assign each subinterface to a VLAN using the encapsulation.1q command. This command specifies which VLAN the subinterface belongs to. For instance, encapsulation.1Q10 would associate the subinterface with VLAN 10. Then, assign an IP address to each subinterface. This IP address serves as the default gateway for devices in that VLAN. For example, IP address 192.168.10.1, which has CIDR notation 255.255.255.0, assigns an IP address to the subinterface for VLAN 10. On the switch side, configure the interface connected to the router as a trunk port using the switch port mode trunk command. This allows the port to carry traffic for multiple VLANs. Finally, verify the configuration using commands like show IP interface brief and show VLANs to ensure that everything is set up correctly. Proper verification ensures that the router is ready to route traffic between VLANs efficiently. Layer 3 switches simplify Inter-VLAN routing by integrating routing capabilities directly into the switch. Here's how you can set up Inter-VLAN routing on a Layer 3 switch. First, enable IP routing on the switch using the IP routing command. This allows the switch to route traffic between VLANs. Next, create SVIs for each VLAN. An SVI is a virtual interface associated with the VLAN. For example, interface VLAN 10 creates an SVI for VLAN 10. Assign an IP address to each SVI, such as IP address 192.168.10.1 with CIDR notation 255.255.255.0, which serves as the default gateway for devices in that VLAN. For routing between VLANs, you can also configure physical ports as routed ports. Use the no switch port command to convert a switch port to a routed port, allowing it to function like a router interface. This setup centralizes routing functions within the switch, eliminating the need for separate routers and simplifying the network design. It enhances performance and provides a more streamlined approach to network management. Securing your network switch is crucial to protect against unauthorized access and various network attacks. Several security features help achieve this. Port security limits the number of MAC addresses that can connect to a port. This prevents unauthorized devices from gaining access to the network. You can configure port security to allow only specific MAC addresses or a certain number of devices per port. DHCP snooping ensures that only legitimate DHCP servers can assign IP addresses to clients. It designates trusted and untrusted ports, blocking DHCP responses from untrusted ports to prevent rogue DHCP attacks. Dynamic ARP inspection (DAI) prevents ARP spoofing, where attackers can intercept or manipulate network traffic. DAI checks ARP packets against the DHCP snooping binding table to ensure they are legitimate. IP Source Guard filters IP traffic based on the DHCP snooping binding database, preventing IP address spoofing by ensuring that devices use only their assigned IP addresses. Storm Control protects the network from traffic storms caused by excessive broadcast, multicast, or unknown unicast traffic. It allows you to set thresholds and actions to take when traffic exceeds these thresholds, such as shutting down the port or sending an alert. Implementing these security features enhances the overall security and integrity of your network, protecting it from various threats and ensuring reliable network operations. DHCP snooping is a security feature that prevents unauthorized DHCP servers from assigning IP addresses to clients. This helps protect the network from rogue DHCP attacks, where an attacker sets up a fake DHCP server to disrupt network operations or intercept traffic. To enable DHCP snooping, start by globally enabling the feature with the IPDCP snooping command. Then, specify the VLANs to protect using the IPE snooping VLAN range command. Mark ports connected to legitimate DHCP servers as trusted using the IPE snooping trust command. When DHCP snooping is active, the switch intercepts DHCP messages and only allows responses from trusted ports. This ensures that clients receive IP addresses only from legitimate DHCP servers, enhancing network security and reliability. Dynamic ARP inspection (DAI) is designed to prevent ARP spoofing attacks, where an attacker can intercept or redirect network traffic by sending false ARP messages. DAI works by verifying ARP packets against the DHCP Snooping binding table, ensuring that only valid ARP responses are allowed. To enable DAI, use the IP ARP inspection VLAN range command to specify the VLANs to protect. Mark trusted interfaces with the IP ARP inspection trust command to allow ARP traffic from legitimate sources. DAI inspects ARP packets and verifies their authenticity before allowing them into the network. This prevents attackers from using ARP spoofing techniques to intercept or manipulate network traffic, enhancing overall network security. IP Source Guard prevents IP address spoofing by filtering traffic based on the DHCP Snooping binding database. When enabled, the switch checks incoming packets to ensure they match the IP and MAC address pairs in the binding table. If a packet doesn't match, it is dropped. To enable IP Source Guard, use the IP Verify Source command. For static IP addresses, you can manually add entries to the binding table using the IP Source Binding command. IP Source Guard helps maintain network integrity by ensuring that devices use only their assigned IP addresses. This prevents attackers from spoofing IP addresses to gain unauthorized access or disrupt network operations. Storm Control protects the network from traffic storms caused by broadcast, multicast, or unknown unicast traffic. These storms can overwhelm network resources, leading to degraded performance or outages. Storm Control is configured on a purport basis and allows you to set traffic thresholds. When traffic exceeds the configured threshold, the switch takes action, such as shutting down the port or sending an alert. Use the Storm Control command to specify the traffic type and threshold level. Regular monitoring and adjustments ensure that Storm Control effectively protects the network from excessive traffic. This helps maintain network performance and prevents disruptions caused by traffic storms. Private VLANs provide additional isolation within a VLAN, enhancing security and control. VLANs are divided into primary VLANs, isolated VLANs, and community VLANs. A primary VLAN can communicate with all other VLANs within the PVLAN. Isolated VLANs cannot communicate with any other VLANs except the primary VLAN. Community VLANs can communicate with each other and the primary VLAN but not with isolated VLANs. To configure VLANs, start by creating the primary and secondary VLANs using the private VLAN command. Assign ports to the appropriate VLAN type. VLANs are useful in environments where additional segmentation and isolation are required, such as in data centers or secure network segments. Switch stacking allows you to manage multiple switches as a single logical unit, simplifying network management. Cisco's StackWise technology, for example, enables up to 9 switches to be connected and managed as one. In a switch stack, one switch acts as the stack master, controlling the entire stack. The other switches, known as stack members, take their configuration from the master. This setup provides redundancy, as a standby master can take over if the primary master fails. Switch stacking reduces the complexity of managing individual switches and provides a single point of management for configuration and monitoring. This makes it easier to manage large networks and ensures consistent configuration across all switches in the stack. Power over Ethernet (PoE) allows switches to deliver power to devices like IP phones, wireless access points, and cameras over the same Ethernet cables used for data transmission. This simplifies installation by eliminating the need for separate power supplies and outlets. PoE standards include IEEE 802.3af PoE, providing up to 15.4 watts, IEEE 802.3at PoE+, providing up to 30 watts, and IEEE 802.3bt PoE++, providing up to 100 watts. Configuring PoE involves enabling or disabling PoE on specific ports using the Power Inline command and monitoring power usage with the Show Power Inline command. PoE is particularly useful in environments where installing additional power sources is impractical. It ensures that devices receive both power and data through a single cable, simplifying network setup and reducing costs. Quality of Service (QoS) ensures that critical network traffic, such as voice and video, gets priority over less important traffic. This helps maintain the performance and reliability of essential applications. QoS involves several steps: classifying and marking traffic, assigning it to different queues, and managing congestion. Traffic can be classified using Layer 2 COS or Layer 3 DHCP markings. Once classified, traffic is placed into queues with higher priority traffic getting faster service. Policing and shaping mechanisms control the rate of traffic, ensuring that network resources are used efficiently. AutoQoS simplifies QoS configuration for common scenarios, making it easier to implement QoS policies. QoS is essential in environments where multiple types of traffic compete for network resources. By prioritizing critical traffic, QoS ensures that important applications perform optimally, even during times of high network usage. Effective troubleshooting is key to maintaining a healthy network. Common issues include VLAN misconfigurations, STP loops, port security violations, and performance problems. Start by checking port status and configurations using commands like show interfaces status and show port security. Ensure that VLANs are correctly configured and that ports are assigned to the appropriate VLANs. For STP issues, verify the root bridge, check for loops, and ensure that all ports are in the correct state using show spanning tree. Monitor CPU and memory usage to identify performance bottlenecks. Security features like port security, DHCP Snooping, and DAI can generate logs that provide insights into potential threats. Regularly review these logs to detect and mitigate security issues. By systematically checking configurations and using the appropriate verification commands, you can quickly identify and resolve network issues, ensuring smooth and reliable network operations. Familiarity with essential switching commands is crucial for effective network management. Here are some key commands. Show MAC address table displays the MAC address table. Show VLAN brief shows VLAN configuration details. Show interfaces trunk displays trunk port details. Show spanning tree provides STP status and configuration. Show EtherChannel summary summarizes EtherChannel information. Show interfaces status displays interface status and configurations. Show processes CPU monitors CPU usage. Show processes memory monitors memory usage. Show port security provides port security details. Regular use of these commands helps in monitoring network performance, diagnosing issues, and ensuring that configurations are correct. They are essential tools for any network administrator. Switch hardening involves implementing best practices to secure the network and protect it from threats. Here are some key practices. Disable unused ports to prevent unauthorized access using shutdown on unused interfaces. Secure management access by using SSH instead of Telnet and implementing AAA, authentication, authorization, and accounting for access control. Use strong passwords and the service password encryption command to protect them. Control plane policing helps protect the switch CPU from excessive traffic, ensuring it remains responsive. Disable unnecessary services like CDP, no CDP run, and small servers to reduce attack surfaces. For VLANs, use separate VLANs for management and avoid using VLAN1. Regularly update the switch's iOS to patch security vulnerabilities. By following these best practices, you can significantly enhance the security and resilience of your network. The networking field is continuously evolving with new technologies that enhance performance and management. Here are some emerging technologies. Intent-based networking allows for policy-driven network management, making it easier to implement and enforce network policies. AI and machine learning are increasingly being used for network management, providing predictive analysis and automated troubleshooting. Programmability through APIs and Python scripting enables network automation, reducing manual configuration efforts. Software-defined access (SD access) from Cisco is a modern approach to campus networking, simplifying network management and enhancing security. Wi-Fi 6, 802.11ax provides higher throughput and improved efficiency, increasing the demand for better switch uplinks. Integration of Internet of Things, IoT devices requires robust PoE capabilities and enhanced security features. Keeping abreast of these emerging technologies helps ensure that your network is ready for future demands and can leverage the latest advancements for optimal performance and management. If you're preparing for the CCNA exam, focusing on switching concepts is essential. Here are some tips. Pay special attention to VLANs, STP, EtherChannel, and Inter-VLAN Routing. Hands-on lab practice is crucial, so spend time configuring and troubleshooting switches. Be prepared for troubleshooting scenarios, as diagnosing and resolving common issues is a key part of the exam. Mastering commands like show and configuration commands is important, as you'll need to use them frequently. Understand the underlying concepts behind configurations to answer theoretical questions confidently. Practice time management to ensure you can complete all tasks within the exam time limit. Use official Cisco materials and practice exams to familiarize yourself with the exam format and content. By following these tips and focusing on practical and theoretical knowledge, you can increase your chances of success in the CCNA exam.